Okay, well, this morning I will talk about multiple features in AllegroGraph, but the real focus will be on social network analysis. I'm clicking here on my PowerPoint and it doesn't go forward. Okay. Here is the contents of my talk this morning. I will first spend a few minutes about what is new in AllegroGraph 3.0, and as always I promise to do that within 5 minutes. Then I will start with my social network analysis. Actually, our social network analysis is part of a bigger story. We call it the event database story. So before I really go into social network analysis, I'll also talk a little bit about AllegroGraph as an event database. Then I go into what social network analysis actually tries to address. So I'll go through a list of 4 questions. Once I've done that, I will go a little bit deeper on the technical level, and I will describe some of the graph analysis that we do. And then I hope to spend most of my time on 2 demos. One demo is a demo about a database of friendship and love. The other one is a demo with some social network analysis on the DBpedia, which probably most of you know, but if you don't know it, it's an RDF-ified version of the Wikipedia. And if you want to see this again, you can go to our website, or you can visit us at Semtech, which will be in from May 19th to 22nd in San Jose. Or we'll also be in Java 1 tomorrow, where I'll talk about the semantic panel, again about social network analysis. Okay, so first, AllegroGraph and what is new in AllegroGraph. If we look at the people that signed up for this webinar, I see that roughly half of them is a first-time visitor. The other half has seen this thing before. So just very shortly, AllegroGraph is to some extent a traditional Triplestore or graph store. We are scalable and persistent. If we use our federation feature, we can load easily 10 billion quads on affordable hardware. One special thing that we have in our Triplestore is that we do range queries. So if you have anything with numbers or dates or telephone numbers, then we encode them in a very efficient way so that you get the same efficiency as relational databases with range queries. We comply with all the W3C standards for RDF and RDFs and OWL and Triplestores. You can use AllegroGraph as a standalone engine if you want to do analytics, but you can also use it as a real-time server in client-server mode. We do our own reasoning, but if you want to, you can also hook it up to Racer. We work with partners for graphical user interfaces, so both Top8 Composer and Racer Porter will work. And we have full-text indexing on our Triplestore, so if you have objects in your triples that contain human-readable text, then we will do full-text indexing on it, and later on I'll show you why that's really handy to have. And further on, we provide name graphs. So this is just AllegroGraph as a traditional Triplestore, and then we have some new features. And for one time in my life, I want to use one of these crazy PowerPoint titles. So what are the new features? Well, first, in 3.0 we have federation, which means that you can now say load triples in in separate databases. But then if you want to query them, you just create one abstract store and you tell the system all the other stores that belong to the federation, and then you can transparently use a Prolog or Sparkler reasoning against that abstract store. It will both work for remote Triplestores, where the Triplestores are distributed all over the web, or within your data warehouse, or even on one machine. Then the other thing, and we'll have new webinars about this later, is we included in our Triplestore also a new way to encode geospatial latitude longitudes. We have some kind of an R3 representation, and we are just as efficient as spatial databases for finding, say, bounding boxes. And we do the basic polygon handling. Then we do temporal reasoning, so we make it very easy to reason about time, say the time of events. And then, of course, today we do the social network analytics. I won't say anything about that. And part of what I do today is also show for the first time Graph, our new navigation tool for large triple stores. I'm kind of sorry about the name. If anyone can come up with a better name for our graphical user interface, then we're welcome to suggestions. And finally, in the near future, we'll also talk about an Oracle connection that we now have, so we can work with Oracle 11g, and we work on Python, Ruby, and C# interfaces. So this is about what is new in AllegroGraph. Now let's go to social network analysis. Oh, sorry. One thing I forgot to say is that with our Triplestore also comes for, well, the Triplestore was written in Lisp, but most of our customers use it from Java, and so we've written several tens of examples of how to use the Triplestore. So we have a whole list of tutorials. The address is at the bottom. I actually can go to that. Let me go to the site itself. So what you can do is you can go to the Learning Center. I think it's actually up and running now. And for example, you can go to any of these examples and you'll get an example of, say, how the generators in our social network analysis work. So I would suggest that you, after the seminar, if you're interested, well, here's all the information that you need to get going. Okay, so I'm back to the presentation. And let's see here. Okay, so what I said in the introduction is that social network analysis is part of our story about AllegroGraph as an event database. So we have several customers that are using the current version of the Triplestore to do queries like you see here in black. Find all meetings that happened in May within 5 miles of Berkeley that was attended by the most important person in Janss's friends and friends of friends. So what you see here is a query that combines social network analysis, geospatial, and temporal reasoning, and we can do that all in one query language. Now before I show you the query language, a little bit about the events. So what we've done is we've created a very simple event ontology. Basically we're saying that an event is a thing that at least has a type, and there's all kinds of events. There's meetings, communications events like an email or a call detail record in a telecom database. There's financial transactions, attacks or truths, insurance claims, etc., etc. And if you want to deal with that, you need at least some RDFS++ reasoning. Then most events in this list also contain actors. So in setting you will have multiple actors. In an email you will at least have 2 actors, the sender, but then there might be a list of people that you send it to. Financial transactions have multiple actors, etc., etc. And then most things happen at a particular place, so that's why we have the geospatial reasoning. Most events start at a particular time, and sometimes they also end, and so you have durations, and we have a whole library that makes it easy to use these times and durations. And then of course events are defined by everything else that you can say about that particular event. If you look at the world from the perspective of events, you actually see that they're almost everywhere. If you just take healthcare, if you look at healthcare, well, every hospital visit, every visit to a drugstore, every medical procedure, every entry into the hospital, it's all an event. And I won't even go through the list, but just give you this list, and if you think about it, you'll see that almost everywhere you'll find things that you can work with as if they were events. So then I show you the query again that I talked about earlier. Find all the meetings, etc., etc. And this is how a query language looks like to do this particular query. It might take a little bit. If you're familiar with Sparkle, then actually you won't find this too hard. Let me just explain it. So basically you say, well, find every X where there is an ego group around the person Jans, according to a generator of people that Jans knows. Put them in a group and make sure that you get an ego group that's not deeper than 2 layers. So actually it's friends and friends of friends. Then we have another functor that says, okay, well, find every person X within this group and start with the most important person in that group, according to this statistics called actor centrality. And then for every X that you find all the events that I have about this X in the database. And then for every of these events, only find the ones that are a meetings that actually happened between these 2 dates. And then also find only those meetings that happened within Berkeley within 5 miles. So if you look at this particular query, what you see again is that you combine social network analysis. This is just a simple database lookup. Here you do a little bit of reasoning because you might have informal meetings, interviews, and what do you have? So in this case you have a little hierarchy of types of meetings. Then you have some temporal and some spatial clauses. Yeah. So social network analysis is part of this story where we can do all these things together. But today we'll only talk about the social part. Now, if you want to get familiar with social network analysis, there's a wonderful introduction on the web to be found at this link that I show you there. Actually, it's a summer course that you can follow. It takes 6 weeks. It's done in Essex, and they have all the material for the course online. So wonderful pictures, and you might find it worthwhile to go there. Also, there's a lot of books currently about social network analysis. This book on the left, called the slightly grey-blue one, is more like a historic overview of social network analysis. It actually started already in the 30s. It was tough work doing graph analysis on paper. This book, the red one, is the Bible of social network analysis. Basically contains almost all the algorithms that you do within social network analysis. The third book is a book that's fairly recent. I think it's 2007. Yes, 2007. And it's about how you can use social network, how you can make interesting social network applications on the semantic web. And finally, this is a 2007 book about mining graph data. All interesting books if you're interested in this particular topic. Well, if we just think about the graphs that we work about, just to keep these ones in mind. One type of graph would be, say, high school friends, where the yellow are the girls, the green the boys, and the red the sexual active guys. Or a graph with political books, where you look at the references within books and how they refer to each other. And the wonderful thing about books in the US is you have Democratic books, Republican books, and never the twain shall meet. Anyway, let's go into what are the things that you try to achieve with social network analysis, or better said, what are the questions that you try to answer? Well, the first question that we have functions for is, how far is a particular person from another person? So it's the well-known degrees of separation. And the other one is, okay, I can find maybe a link from person 1 to person 2, but what is the connection strength? So you could count the number of shortest paths between them, or you could have weights on your links, and you could even compute the overall weight. It's up to you to how you want to compute the connection strength, but at least it's one of the things that you can do with our library. Then the second question is, say you have a particular person, but in what groups are these persons? Yeah. So, and there's 2 groups that we usually talk about. One of the groups is the ego networks. Those are all the people, well, most basically, those are your friends or the friends of your friends. Or you have fully connected graphs. So that are graphs where everyone is connected. So in my case, I have, for example, a family clique where I know everyone, of course, in my family, but also the closest friends of everyone in my family. And I have a tennis clique, and I have a work clique, and well, I could go on, but you get the idea. This is one of the important clicks that marketeers worry about and care about. Then okay, so you have a group, and now you would like to know, okay, what are the key players in my particular network? So there's several statistics that we provide. One would be, say you have a group of people and you know the connections between them, then one statistic for how important you are is if you have the most connections in the group. The other one would be if you would have a group and you take the shortest path between everyone in the group, then you could kind of compute who's got on average the shortest path to everyone else. And then the third one is, okay, take the shortest path between everyone in the group and then find if you are on more times on a particular shortest path than anyone else. If you are the most important person in the group. So again, I will show you later this in the demo. If you look at active degree centrality, just as an example, and you look at the circle, then well, all degrees are of course the same. If we look at the star, then you see that if you're in the middle, you're really important. People here are less important. And if you have a line group, well, it kind of depends. If you're at the end, you're not really important, and in the middle, you're a little bit more important. Again, I will get back to this when I show you how you call the functions and what these functions do. So let's skip the actor closeness centrality, because I will get back to that one. And the actor betweenness centrality. So then the fourth question you try to answer with social network analysis is, does a group have a leader, and is the group cohesive? So, well, the first question is about group centralization, how centralized is this group, and the other one is how strong and well connected is everyone in the group. I mean, you might have a sparse group, or you might have a group where almost everyone is connected. Again, you can imagine from a marketing perspective why that would be an important question to have, an important statistic to have. So, before we go into the demo, I want to talk about some technical concepts. I think that almost everyone in the audience will be somewhat familiar with graphs and graph theory.
Here's a question that might be better asked now. Is the semantic distance both geo and temporal, or is it based on relationship type, or a combination of both?
Can you repeat that entire question?
Is semantic distance both geo and temporal, or is it based on relationship type, or a combination of both? It's asking about the semantic distance.
Well, if you talk about the semantic distance, then you usually have to specify yourself what the links are that you want to follow from one person to the other. And then we only look at the types of links, and if you want to, you can put weights on the links. We provide also the spatial distance between people, and you could use that if you wanted to as one of the semantic links between people. But right now, yeah, I've never done that. I probably could solve that with generators. And if it's important, we'll figure something out.
Okay, we'll look at
to make that work.
Thank you.
Yeah, so again, I guess that most people in the audience know about directed graph and undirected graphs. And what I see most of the things that we do is with undirected graphs. But again, in our system, both things work. The other thing is our social network analysis will work both in one-mode networks and two-mode networks. So if you have groups where every person or everything, no, let's talk about persons here, where every person connects directly to other people, then we talk about a one-mode network. We talk about a two-mode network if we, for example, would talk about an actor and a movie database, where actors have movies and movies have actors. And so you don't point directly from actor to actor, because you always have to go through a movie. And you can't go from movie to movie because you have to go through actors. So then we have two-mode networks. But for our social network analysis, it doesn't make much of a difference because we have generators to deal with how you go from one node to the next node. So that brings me to the next point, which is the generators. Those are the most important thing to understand in how we do social network analysis. Generators are functions that know how to expand nodes. So, I mean, if you do graph search, basically you want to go from one goal node, say, to a destination node, and you have to decide beforehand which type of links you want to traverse, because you might have many different types of links, and not always do you want to go through every link, although you could. But usually you want to make a sub-selection or selection, and the generator will just do that. The generator will also make sure that if you have a two-mode network, that say you want to go from actor to actor in an actor movie database, is that you, in the generator, bypass the movie and get direct links from one actor to the other. I'll talk about that later. Our generators are fully functional, so they can be even complex Sparkle or Prolo queries. And then the generators are actually functions that are input to search functions and social network analysis functions. So every search function that we have and every SNA function that we have can use these generators. Just to give you an example, say I have a little graph where A had dinner with B, A kissed with C, C had a movie with E, B kissed with D, D went to a movie with E, and E had a dinner with A. This is a little bit of a graph from my database of friendship and love, which I will demo later, but just take this little graph. Now, how do you get from A to E? Well, the obvious way would be go from A to B through dinner with, then from B to D with kissed with, and then from D to E with movie with. Or actually, you also could just go from the A at the end here to the E. I hope you guys can keep up with my cursor on the screen, by the way. So if we want to write a generator, and say we write a generator called knows, then what I would say is, okay, whenever I have a node, take all the objects of the triples that I get with where the node is a subject. Well, in graph language, if you have a node, take all the things that dinner with points to. Well, in this case, this generator knows would not get me to from A to E, because, well, A gets me to B, but that's it, there's no other one. And here I have, at the end, I have A dinner with E, but I'm only pointing outwards. So we also can write a generator. So the next generator, the next version, would say, well, take all the things that I point to outgoing from the node or incoming to the node. And now suddenly I will find a link from A to E, because now suddenly I can get to the last part of the graph, and I will find that A points directly to E backwards. Now if I wanted to go through all the links, I could write this particular generator, the long one. I hope you can see my mouse, the first one. And this generator would go through all the dinner with, movie with, and kissed with in both directions. And we have a shorthand notation for that, so I can say, okay, take the undirected versions of dinner with, movie with, and kissed with. Yeah, I hope this is clear. Any questions? If this is too confusing?
There are a couple.
Let me see. How would you manage subgroups if it will be included in the SNA? When we do the demo, we'll give you various ideas of how you can work with subgroups. And the next question is, do generators operate at data load time or at query time? The answer to that is that you can generators whenever you want. You can write them as beforehand. before you even loaded your triples, you already can define a generator. But even when the data is loaded and just before your query, you can also do that. And in our case, within our selectWing language, you probably even during the query could define a generator if you wanted to. But that's a rather advanced topic. Okay, let's continue. And finally, what I want to show is that you even could put Prolog or Sparkle in the generator. So here you see the generator nodes where you say, okay, follow only those nodes where I went to the movie with someone and I dinner with someone, but I did not kiss with that particular person. Or go if someone else went to the movie with me or kissed me, or well, I did not kiss me. Well, just read the query, you get the idea. Yes, so you can have complex queries within your generators. And the whole point is, as long as you return the list of children of the node, then our search functions and SNA functions will be okay. So this is an example of a general search function, and I'll demo all this, but just look at this one. This is a bidirectional search, where if you specify an A node and a B node, it will use the generator to work both from A and B at the same time to find a point somewhere in the middle. In most cases, this is also the fastest way to do our shortest path. So in our shortest path functions, we actually use the bidirectional search. So this is the general search function. And then we have a number of social network analysis functions. I'll just give you some examples, but given that I'm going to demo them, I probably can just skip them for now, but for completeness, I will leave them in this presentation, which we'll put on our website later. And then, as I showed you before, all these social network analysis tools can be embedded in the query language. So here's an example where you generated a nose generator, and then here you would create a query where you find the people that Jan's knows, to say to the second degree, and then find all the places that X is in, and then find a box around that particular place. Now, one question I get all the time, why is this not in Sparkle? And actually, we are working on that. The problem is Sparkle only allows you to have 2 arguments per predicate. So one way out of that is to have magic predicates, where you specify clauses where the predicate is actually smart, and where you kind of make a fake language so that the compiler can look at the predicates and make queries that have more arguments. But before we go that direction, I am talking to several people in the Semantic Web community to see if we can get to some standard way of dealing with with predicates with multiple arguments. So
there was a question: does Sparkle have a concept like generators?
Well, in Sparkle, the filter is the tester, and in Sparkle, nearly every class that has a variable that is unbound so far is a generator. And if you have a Sparkle class where all the variables are known, then that would be a filter. So let me start with the demos. So the first demo I do is a kind of a funny demo. It's a database of friendship and love. So I have created a database with 5,000 people, where each person knows on average 40 other people. Then of that you have a sub-selection that you shook hands with, roughly 35, and then a sub-selection of that you went to a restaurant with, and then a sub-selection of that you went to the movie with, and then a much smaller number you kissed with, and a very small number you were intimate with. Yeah, so you can imagine what kind of graph you get. And let me start now going to do this particular demo. So let me go here. And now, So as I mentioned before, all the social network analysis techniques are callable from Java, but for this particular demo I'll do a little Lisp demo. And just to get you going on what's happening here, I will start with how you create triples in the Triplestore and how you get them out again. So just as a 2-minute demo, how do we create a Triplestore? Well, we say create Triplestore, and because I hate typing long names, I registered the namespace O to stand for this long URI, and so now I can type things as O person1. By the way, on the right hand side I have an editor with forms, and basically I go through these forms step by step. On the left hand side you see the listener. So what I basically do, I hit a button in the editor, it will send it over to the listener, it will execute it. Yeah, so you see the interpreted code. So let's add some triples. So for example, I add the first triple, person1 as the first name Steve. On the left hand side you now see 1, meaning that was triple number 1. And I add a triple, person1 is an organizer, and person1 age is 52. And then I talk about person 2, which is the first name Jans, who is a psychologist, and he's 49. And I say that person 1 is a colleague of person 2, and let me see, and here is the graph, the little graph of all the triples that you have right now in the database. If you are a person that likes text more, then you can just say, give me all the triples. Well, this is a little bit an unpleasant way, so let's print them one at a time. So here are all the triples in the Triplestore. Now say I want to get triples out where the predicate is first name. So basically I'm saying give me every triple where the predicate is first name. I do that and I find there's a person 1 with the first name Steve and a person 2 with the first name Jans. I can take one triple, so I say set a triple to the first of the triples list. So now I've identified one triple here on the left hand side, and I hope that the webinar software is keeping up with this. So we have one triple, and I can say, okay, what is the subject of the triple? Well, that is of course person 1, and the predicate of the triple is the first name. The object of the triple is Steve. We have a fourth argument which we call the graph argument, which in this case is just a default number because I didn't specify it. And every triple also has a triple ID, so in this case it's triple number 1. Yeah, so this is just the triples that we have. Then we can also delete triples, so I say delete triples where the subject is person 2, and if I now show the store again, you see that we lost person 2. Okay, so I close the Triplestore. We also, just for fun, for something bigger, we have the Kennedy dynasty in a little Triplestore. So it's 1200 triples. I load it. 47 milliseconds later, it's loaded. I could say show me everyone that which is person 1, and I get some some triples back that are all about the first Kennedy in the Kennedy dynasty. And here actually, and I hope it's keeping up with that, here you see that there is a person 1. So what I'm showing you here, the graphical thing, is what we call graph. And again, please come up with a better name. Maybe we should award a prize for a better name for this thing. So you see that person 1, and the whole point of this graphical user interface is to navigate through Triplestores. And the one design choice we made is that we also want to have everything readable. So we go for readable and not for having as many triples as we can on the screen. Say I look at a particular person 4 here, then there's two things I could do. I could say show me all the things that I know about this guy, and I could say okay, I also want to say as child, and I say okay, and I could now do F, and I get a slightly more complex graph. So now you have the has-child relationships, and I can click on anyone and I can do a T. I hit the T, and now I have another way to browse through the Triplestore. So I could look at person 2, and for person 2 I say, okay, I want to see person 13, 15, 17 and 3. I could do 2 again. And now where's person 2? Oh, person 2 suddenly will have the children. Oh, she already had them. Anyway, the point I want to make, there's both a graph way to look at your triples, and there is a tabular way to look at your triples. And you can, if you follow the graph long enough, you can basically get wherever you want in the Triplestore. Person 17, person 74, person 18, and you go back and forth. Okay, this is about basically graph, the graphical editor that we have. Now let's go back to social network analysis. Here. So today I will not talk about Sparkle or Prolog or text indexing or geospatial, but let me find the social network. Not about temporal here, social network analysis. So I'm opening a Triplestore, read-only in this case, with roughly 500,000 triples. To show the triple count of this thing is this 5.5 million triples in this database. And just to get a feel for what's in the database, let's go to the graphical user interface again. So let me get rid of the old ones, clear and uncache everything, and then find all the names. Or I can just say, let's look at person 0 and say I want to explore this particular person, and I only want to look at the most interesting relationships, which is intimate with and kissed with, both incoming and outgoing. Yeah, so now if I hit in the editor the F button, you will see a graph of who you connected with. The blue lines are, if you look at the bottom, kissed with. The dashed ones are kissed with, intimate with, and the purely black ones are only intimate with. I still can look at person T in the other way, and you'll see that there's a bunch of people that he ate with, only 2 that he was a few that he was intimate with, a few that he was kissed with, a lot of people that he knew or knows. Yeah, so you get an idea that we know a lot, but we only show a few of them. So now one thing would be, let's create another person. Say person 100. So we have person 100. And one of the things that we want to see is, can we get a connection between person 100 and person 0 through the intimate relationships? So let's see. I look at that, no connection. I look at that, still no connection. Okay, now it's getting kind of busy. So let's get rid of all the leaves that don't point to anything. And yes, what you see, I now get from person 100 through this person, this person, this person, finally to person 0. Yeah, so you can do a little bit of looking through your graphs to find things visually, but now let's go to the programmatic way of finding connections between people. So I talked about generators. Yeah, so here's how I make a generator. So I say define an SNA generator, and I call this thing nose. And it's undirected, so only follow the nose links. Actually, I call this for shorthand, I will call this KN, means nose, and then intimate will be IN. So the other one I make is the intimate connector, which is the undirected relationship over intimate with. And how this works is, okay, just take, say, a person 0, yeah? What I do is I apply the function intimate to person 0, and I get a bunch of people here on the left. Now, again, this always looks better in the visual interface. So here, all the people around person 0. So one person in the audience wanted to know about groups. This is how you create groups, for example. So how many people do you know or know you in this database? Well, I can say what is the length of this group, which would be 72. If I use the know generator, if I look at the intimate relation, there's only 8 people that I was intimate with, or was intimate with me, according to these relationships. Okay, so we looked at what a generator is, or what a generator does. Now let's look at the function that use it. So one thing we could do, we could say, okay, let's go from person 0 to person 100, and let's use the know generator, and let's see if we can find a connection between the two within 3 steps. So that's the breadth first search. And I look at the list, and I get one list going from person 0 to this to person 100. If I try to do the same search, but I use the intimate connector within 3 steps, then I probably won't find anything. So if I would make this deeper, say 7, doing a breadth first search, and I hope that people are familiar with breadth searches, then you will find something. We also provide, I was doing this, depth first search. Yeah, so can I go completely depth first from person 1 to 0 to 100? Well, if I use the know relationship, there's so many links that I always will find something. But if I want to follow that using the intimate connection, it takes a lot longer. And then finally we have the bidirectional search that we usually use for the shortest path, where you actually start at the both ends of what you were looking for, and then you work in circles around until the circles somewhere meet, and then we find an easy step. And again, we need a much deeper level if we start to use the intimate generator here. And just for fun, let's see when we start finding the shortest path between 2 people. So I say loop for I from 1 to 6, print a line with I, and then print whether or not there's a path. So if I do that, I find that there's no links between 1, 2, 3, or 4 levels deep, and only at 5 and 6 will we find a shortest path. Now in general, the average shortest path in my graph, if I use the intimate relationship, is 5.5. If I use the knows relationship, it's the average shortest path is 3.7. So those are the search functions. Now let's go to the social network analysis functions. So I create a new type of generator called links, which again is an undirected one over a predicate that I still have to define, called SNA links to. And don't watch this particular guy here. And what I'm going to do is I'm going to create a number of groups, and for each group I'm going to compute the actor degree centrality, the actor closeness centrality, and the actor betweenness centrality that I talked about when I was showing you my PowerPoint. So I'm going to do that for a particular group. So let's show how that works. So first let's build a star graph. Yeah. So we have a star graph of 11 nodes. So here's the star graph, 0 in the middle, and then everyone else is connected to that middle star. So now let's print the actor importance of every actor in that little group. So what you see is in the star graph, person 10 to 0 all have the same importance because they're all at the end of the star, and only person 1 is super important, yeah, because he's in the middle. And so sorry, the first column is for the degree centrality, the second one was the closeness centrality, and the third one was betweenness centrality. Let's do the same thing for a line graph. So I create a line graph. Let's show how the line looks like. This is the line. It's not a pretty line, but it's a line. And the actor importance, and what we see now is that actually the people at the end are relatively unimportant, and the people in the middle are more important. Now for if you only look at the degrees, everyone is the same here. But if you look at the average shortest path, say, then you get these measures. Then in the middle, you're really important. And then we can make circle graphs. So let's make a circle graph of 11. Again, I've seen prettier circles in my life, but at least this is a circle. And if we then look at the actor importance, what you see is no one is really important in the circle, or everyone is really important in the circle. So all the measures give you basically the same data. Now I could go on with this and do all these measures again on the groups. So I could do my group measures, but actually let's skip to the clicks. So clicks were things that are fully connected graphs. That's one I want to show. So I'm building a little graph. Now you can see how people are connected in this particular graph. So one thing you might want to know is, okay, find all the clicks around person 1. So let's look at it. And we'll find that look at the left of the screen below, there's a click 132 and 134. Because person 1 is in 1, 2, 3 and in 1, 3, 4. If we look at the clicks for person number 3, then he's got many more clicks. So we take only the clicks that have a minimum size of 4. And then we find that there's 1, 3, 6, 5, 4. So if we look at person 3 here, we see that there's 1 where he's connected to 4, to 5, to 6, and 5 is connected to anyone, and 6 is connected to anyone, and 4 is connected to anyone. So that's the basic statistics that I wanted to show, and then I want to conclude with another fun demo of social network analysis on a much bigger database. So let's close up. I'll get rid of this one for the moment. And so we know with the next one, which is a demo on top of the DBpedia. As I mentioned before, the DBpedia is the RDF version of the Wikipedia. In the version that we show here, we actually have 120 million triples. This is we're using the newest version. We added Sparkle Select Text Indexing, but let's only focus again on the social network analysis. Let's see, where do I have the browser? Actually, first let's look into a version. Let's look for a second at the data. Where is it? So this is the DBpedia, a browser that we have for the DBpedia. For example, here you see Cambridge, and then here you see all the properties and the values. And I could click on Charles Darwin, and I get everything about Charles Darwin. And I can click on the autobiography, and I won't click on England because I get too many things back. Even London, Angleterre, I can go to probably a French part, yeah, a French version of a French page in the Wikipedia. Anyway, so this is roughly the a browser on top of the DBpedia with 120 million triples. Now let's look at one of the movie stars that I want to do my social network analysis on. So I take Kevin Bacon. So I'm doing a text search on Kevin Bacon, and I will get a list of, well, it's a really long list. So let's find the Kevin Bacon that I'm interested in. Oh yeah, here's the Kevin Bacon that I'm interested in. So I'm looking at this one. So here I have all the triples for Kevin Bacon. And actually he's the author of 6degrees.org. He's born in Philadelphia, but I'm much more interested in the movies that he worked in. So here are a bunch of movies that you see. So we basically reap all the various languages that have it in our generator for this. Let's see, is there more? Oh yeah, this is Italian of a number of movies that tell that Kevin Bacon was in these movies. And I'm looking actually for starring of. Oh, and here's another list of movies that he played in. So I can click on, say, Mystic River. I get Mystic River again. There's lots of Chinese and Japanese here. And when I look at that one, I will probably have another starring, and I get people that again play in that movie. And I can look at Sean Penn. So basically, you get an idea of the graph that is in the DBpedia. So now let's go to another demo that actually does some fun stuff with that, and that's in somewhere in my browser. Is it this one? Ah, yes. So I can, for example, say take Matt, say Dillon. I take Matt Dillon and say, did he work with Kevin Bacon? And I search for all the Kevin Bacons. There's one Kevin Bacon. Oh, and I saw they played in the same movie. So Matt Dillon played in Wild Things with Kevin Bacon. Let's see if Kevin Bacon played with Bruce Lee, or how far he is from Bruce Lee. Search. I find multiple links. Let's choose Bruce Lee and Kevin Bacon. I click here, and then I'll get that Bruce Lee played in a movie called Enter the Dragon. Who didn't see this? With a person called Anna Capri in Brotherhood of Satan with L.Q. Jones. Never heard of him. In A Prairie Home Companion with Meryl Streep, who played on River Wild with Kevin Bacon. So I can click now also on, say, one of the actors, and what I get is that a social network summary of this particular Anna Capri. So she has a very small group, an ego group, that is all her direct friends. But if you look at the friends of the friends, it already goes to 642. The degree centrality, let's take another one. Let's take a more interesting one, Bruce Lee. So I'm clicking on Bruce Lee. So there's 25 people in the database that he was connected with, but if you look at their connections, it's much bigger. This is his density here, and here's the density if you look at the much larger group. And within his own group, Bruce Lee is of course very important because he's connected to everyone. If you look in how important he was in the group of friends and the friends of his friends, he's of course got only a few connections, so his degree centrality in that group is much less important. So I could go on. I mean, this is really fun to play with this particular thing, to see how connectors connect from one place to another place, but let's go back to the presentation. No, that's not the one. Yeah. So let me conclude. So we use AllegroGraph for scalable, or AllegroGraph is a Triplestore that will allow you to do scalable graph applications. You can do all kinds of new things with our social network analysis libraries. I'm not saying that what we have right now is perfect, especially if you have measures like closeness centrality and betweenness centrality. Then you do so many shortest paths, especially in bigger groups, that we're still working on making those very efficient on a large group. And so what we actually would like to do is that if people have requests for particular social network analysis algorithms, please just send them in, and we'll put them on the list, prioritize them, and just keep on working to get you more and more of these algorithms and make them faster. So already next month, one of the things that we will hand out as a file that you can download or as a patch is cached ego groups. If you say have an ego group of 8,000 people, then you don't want to do every time go to the Triplestore to find the shortest path. It's probably, oh no, it's so much quicker to cache that group of 8,000 people and do your shortest path on a cached version of those triples. We're working on a thing called eigenvector centrality. It's a measure that's a very high correlation with the centrality measures, but it's infinitely faster. And we're almost done with Google's PageRank algorithm, and so within a month you can expect to have those algorithms too. So with that, I want to conclude this presentation, and I would like to see if people have questions for me.
There are some questions that have been queued up. might be best if just let you read them.
Can we call out to external SNA libraries? Well, right now, you probably mean, can I use algorithms from other social network analysis libraries and apply them to the Triplestore? Well, not directly. You would have to write a converter that takes the data in the Triplestore, puts them into an association graph or one of the things that the other library works with. Another question is, can we specify relationships among the predicates for, e.g., uncle is connected to, say, father of and brother of relationships? Yes, you can put any. So one of the things I sometimes show in my lectures is a whole Prolog program to do family relationships. Actually, you could take every predicate in there and stick them in a generator, and it would just give you uncles and nephew in whatever directory, whatever direction you used it in. So yes, you can use any rule and put them into the generators. Another question: you identify the clicks with numbers. Is there another way to identify them? Numbers seems to be changing when the data changes. Well, yeah, definitely. Well, you're right. You know that finding, say, the biggest click is an NP hard problem. So if your graph is the starting graph where you want to find your click is really big, you have to wait a long time. We have a very clever algorithm to find clicks even on a relatively large group relatively fast. But what we found is you're usually interested in the larger clicks. So we can even specify only compute clicks where the clicks are bigger than, say, 10 and smaller than 20. Just to give you an example, if I take the DBpedia, then Kevin Bacon works with 240 different people. And if I find all the clicks for Kevin Bacon, I get more than 4 million clicks. And so, and that takes 23 seconds. If I just want to get all the clicks that are, say, more than 15, then I get all those bigger clicks in a few seconds. Your work is directly applicable to event processing as well. I don't know what kind of event. I mean, event processing is really an ambiguous term. If you take it to be our type of event processing, basically, as I said, we have an event. Oh,
this follows the same.
Oh, for relationships among events. Sorry, let me repeat the question because otherwise I'm a little bit chaotic here. Your work is directly applicable to event processing as well, and so relationships among events. Yes, the social network analysis seems to suggest that we only talk about relationship between people, but I can show you in the example, the movie browser, that actually I can find a path between movies just as well with the same algorithms, and I can, if I wanted to, I can also compute the social network analysis to movies instead of actors. So if you look at the screen, you see that the Brotherhood of Satan has 28 friends, meaning through the actors that play in that movie, there's 28 other movies that directly connect to Brotherhood of Satan. And so if you have events with people, yeah, you can do the same thing. You can find relationships between events. Okay. Is it possible to define a link if two nodes participated in an event within a certain period of time? Yeah, you can write a generator that actually looks at the time. So you could write a generator where you say, okay, only find the children of this event node when the event node is, well, you could specify that you want to go through an actor or through a particular type, and then you can also specify that the event has to happen between a particular duration or a begin time and an end time. Okay. Why re-implement all the SNA algorithms again? Well, the algorithms are all well known and not that hard to write, and what we want is to make sure that these algorithms, so we're not using new algorithms, we're using just the existing algorithms, but we make sure that they work as efficiently as possible with a persistent Triplestore. Yeah, so we're not writing new algorithms, we're taking the algorithms from the literature, but we tweak them so that we can have them as efficient as possible against the Triplestore. However, that brings up the possibility that it would not be that hard to make subselections of a graph and say put them in a way that UCNet say would like it, or the C-based versions, and so you have an intermediate file where you generate a group and then you can do other libraries and apply them to that group, but then you would have to go through one interaction. Is the AllegroGraph GUI interface available for the Windows OS 64-bit? Yes, it is. What about algorithms that use edge weights, percept edge weights based on recency of interactions? Right now, in the algorithms that we have, we don't explicitly work with weights. In the generator, you could say follow links that have a weight that has a minimum or a maximum. If you are interested in particular SNA algorithms where you actually say want to do an A-star search, then I will be interested to hear what you're interested in, because then we can write functions for the library where we say provide A-star search based on weights in the fourth argument of the triple. Okay, I think we've gotten to the end of the...
Yeah, there are more questions, but
many more questions.
We're running out of time today in the seminar. What we'll do is go through and answer them individually and send them out to you. What I'm doing at this moment is hitting send on an email message I had composed that had a BCC list of all the attendees. It's sending out instructions on how to download version 3, the release candidate 24 of AllegroGraph. We encourage you to load it, use it, give us your feedback. And I want to thank everyone for attending today. Jans, thank you very much.
It's my pleasure.
This concludes today's seminar. Thanks again. See you next time.